Certo.
Boa tarde a todos. Good afternoon, Dr. Lachgar, Dr. Abdou, Lachgar.
Good afternoon. Good afternoon.
It's with great pleasure to introduce Dr. Abdou Lachgar. Is a professor of chemistry at the Center for Energy, Environment, and Sustainability of Wake Forest University and the Bell Faculty Fellow. His teaching expertise is in the general area of inorganic materials chemistry and nanomaterials. His research projects focus on the development and characterization of materials for potential applications in the field of energy, storage, and environment remediation. 3 main projects are underway in his laboratory. The first focus is on the use of the molecular building block approach to the design and preparation of novel cluster-based hybrid inorganic organic materials for hydrogen storage and CO2 sequestration. The second is the synthesis and structural characterization of materials for use as high-capacity cathodes in rechargeable lithium-ion batteries. And the third project has the objective of developing solid acid-base catalyst for the production of biodiesel from inexpensive feedstock such as brown and black grease. Lachgar has authored over 19 papers and he has received over $2 million in grants since he joined the university in August 1991. It's a great pleasure, Dr. Abdou. Thank you very much for stay here in this moment in the sixth chemistry school environment. Chemistry school. It's very interesting for us, your topic of the research. Thank you very much.
Oh, thank you, Luciane, for this amazing, actually, introduction. I want to start by saying that I would rather really be with you there than being online from my office in my university. A couple of years ago, I traveled in Brazil I spent about 4 months in Brazil. I was sponsored by the U.S. State Department through a scholarship or a fellowship called the Fulbright, which many of you may be familiar with. And during those 4 months, I was initially hosted by a wonderful couple that you probably know from UNESP in Araraquara, Dr. Maria Volderin and Dr. Nelson. Both of them hosted me for a while, and then Varnice, she helped me actually organize the whole tour of different universities in Brazil. And one of the things that Varnice organized for me, one of the visits, was to actually come to UFS to visit Luciane and give a presentation. Unfortunately, my wife and I, we were not very much aware of the large distances between different cities. And we ended up visiting Recife, and we had scheduled to visit Fortaleza and Natal. And then it was so difficult until it was not easy to come back to Sergipe and visit with Dr. Luciane. So I had to apologize. And so now that when Luciane contacted me a couple of months ago and told me about this opportunity to speak to you and to share my research with you, I was really, really relieved and happy that I can finally do that. And so, in fact, actually, I organized because of that. Actually, Luciane, maybe my presentation will be a little bit too long because I tried to put two lectures in one. Huh? So let me ask you first: how much time do I have? Do I have an hour? Do I have an hour and a half?
50 minutes. 50 minutes to 1 hour.
Okay. So I'll try to be as quickly as possible, and then I may skip over certain slides. Huh? So the title of my presentation is on solar fuels, and I should probably have phrased it differently. It's really developing solid materials that will play a role of catalysis in order to help generate hydrogen or generate biofuels. That's what really the topic of my talk is, and it's not really just my work. I think without people you see here, Shiba Adhikari is a graduate student in my lab. Zach Hood used to be an undergrad. Now he is a postdoc at Argonne National Lab. Marcus Wright is a collaborator here within our department. And without funding, of course, nothing would have happened. So let me show you first where I am currently. Yeah? So you all, of course, recognize this is the map of United States. Here in red is the state of North Carolina, where Wake Forest University is located. So this is the borders of the state of North Carolina. We we are located in this city called Winston-Salem. Huh? The capital city of this state is Raleigh, but the economic heart of the state is called Charlotte. Is right here. Huh? So this state actually is interesting in many ways because Charlotte is actually the largest banking center in the United States after New York City. So it is probably not very known, but it plays a major role in the economic environment of the United States as a whole. Huh? Well, if I may just share with you things, this is how our mountains. We have mountains and we have oceans, of course. The ocean is right here. The mountains are along this area here. This is how truly our mountains look in late October and the month of November. All these trees change color, beautiful color. I will encourage anyone who is interested to come visit us here during those months. They're just special. And then, of course, we have the ocean. But I must tell you that it is a beautiful ocean, but I still prefer the Brazilian coast to our coast. And not only for the beauty of the Brazilian coast and the vegetations and so on, but also something that I appreciated a lot, my wife and I appreciated a lot when we were visiting there, is the fact that we had caipirinhas and beers right there on the beach. Here you can't. It's impossible.
Abdou, sorry,
Yeah.
Professor.
Yes.
I think it is necessary to put in presentation mode your slide.
It is. I am in a presentation mode.
Oh, is because I think is some problem. The
Is it is it
carros,
is it too small or what?
yes, it's too small.
Well, I am in a presentation mode and I cannot do better than this. So what I could do maybe? Uh, no, not this.
In
Yeah.
the I don't know this one here. It's necessary to click here.
I don't see you. I don't see.
Zeca,
That's very
Zeca,
strange.
help me.
Oi, professora.
Como é que faz aqui para...
Ele tem que compartilhar uma tela específica. Acho que ele fez a apresentação.
Here, but you need to share the particular
Pede para ele apertar o F5 do teclado dele.
press F5. Press F5.
Okay, well,
Press
let me
F5.
So let me go back here. I'm going back to my presentation here, and I'm going to slide from the current slide. So, and you said F5?
F5.
No, it must be function F5 then.
Yes.
No, nothing happened on my side, huh? My screen is completely in full show mode, huh? I am in slide. Now I turned slideshow off. Here I'm turning it on from current slides. I am in a show mode now. Slideshow mode. So when I go to, I'll keep going here. Now I see you, and I see Carlos, and I see Luciane. Okay, I see three of you on the left side, and I see my screen on the right side. Huh?
Yes, yes. But your screen is a little screen. It's not in presentation mode.
Now it's not, but here I will show you what I will go to presentation mode.
Yes.
So I'm going to slideshow. So what do you see now? Do you see any changes?
No, no change.
Well, then I don't know. Then this is bizarre because my screen is on a presentation mode, slideshow.
We can't see the presentation mode. We just see PowerPoint.
Yeah, yeah. So that's very interesting. I don't know. I have here. You are in the, and they said we are in the show. Let me see. Maybe there is another. No, it can't. Yeah.
You press the copy below.
Okay,
if you press the copy below right here. All right.
You mean this one here?
Can you increase the presentation size plus zoom?
Yeah, maybe.
So we can try it.
Let me try this. I'm going to go into slideshow from the current slide, and then let's see how this will work. No, I'm going to back to this.
If you click on the icon down right.
Which icon are you talking about? That I don't.
First, down right. 1, 2, 3, 4. The 4 icons.
You mean in power
near the zoom bar? Near the zoom bar.
I'm trying to look at the zoom bar. Where is the zoom bar? I really don't see.
Below.
Here, what I see on my screen, I am on HTTPS StreamYard.com, yeah? And all I see is microphone, camera, settings, stop screen, and leave studio. That's all I see.
Okay. Continue.
That's all I see. I don't have anything else. I have having issues, questions, question mark.
No problem. Continue. That's okay.
But there are so many pictures that yeah. Well, let's see. Oh, we'll continue and see. But it's unfortunate.
Yes. No problem.
Do you like me to create immediately a Zoom call and send you the link, and then everyone can log on? You can send that link to everyone.
Is it possible, Zé Carlos?
Não entendi o que ele falou, professora.
Que a gente possa migrar para o Zoom, porque ele tem um Zoom profissional, e aí ele pode criar e todo mundo migrar para lá. Pode
Professora,
isso?
eu acredito que não, porque muita gente não tem acesso ao Zoom, ou muita gente ainda não conhece essa ferramenta. Talvez ele peça para ele ampliar o slide, e ele pode ir clicando em cada slide que ele for passando.
I think it's not possible here now, because some people don't have the Zoom. But I possible you increase your slide in Zoom, click in Zoom in your slide, okay. You are talking, it's ready.
It's okay. No, okay. Because the Zoom app, you can download it and install the Zoom app in less than a minute. It doesn't take a long time, huh? Because I'm afraid if there is no, I cannot make my slide bigger than they already are. I just can't. This is the maximum I can do. There is one other options actually, and this is when I go here. I can, but that will take so long. So I can, for instance, put this and then zoom on that. Do you see it bigger now? Do you see the map, for instance, bigger now?
Yes. Zé Carlos, será que ele consegue aumentar a tela?
Ele peça para ele tentar, professora.
Try increase your como é, agora até eu esqueci o que é, como é tela. Diz aí, Zé Carlos, me ajuda. Screen. Can I increase your screen?
If this is the slide is occupying all my screen right now. The slide that says the title, Where Am I? The whole slide is occupying all my screen.
Okay. It's good. It's good. Yes, it's very good. Continue, Dr. Abdou.
Oh, thank you.
The worst is the pandemic.
That's perfect. I appreciate that. Anyway,
can you show each slide of the presentation mode and talk about it? Yes, this mode, each slide. Can you talk about? That's okay.
You mean you want me to talk in this? You don't want me to be on a slideshow?
Each slide. No presentation mode.
Yeah?
So you presentation, you present each slide in this mode. You are here.
Oh, I see. And they can make them try to make them bigger here.
Yeah.
Okay, let me first collapse the ribbon so we can collapse the ribbon.
Okay.
And then try to make it even bigger. Yeah. Okay, like this, huh?
Yeah.
Is that better?
Yeah.
Yes.
Okay. Let's go back here.
Yes. It's much better.
Okay. Then
Okay.
I will use my pen here. So I have a, because in presentation mode I can use the laser pointer, but not in this mode. In this mode I have to use the pen. So do you see my pen here? Or maybe you do. Do you see where do you see this moving around? Anybody sees it? No?
Yes, the blue sea. Yes.
Yeah. Okay.
Everything okay.
Okay, good. Anyway, let's move on and maybe tell you a little bit about Wake Forest University. So this is a primarily an undergraduate institution, but we have a very strong graduate program. So the university was founded back in 1834, and it has very much ranked on the top 30 national universities in the United States. Last year, we were number 13th in the best undergraduate teaching experience. Huh? Now, the reason I put actually this slide is to share information with potential graduate students, those students who may be interested to come and join our graduate program. We pay, once you are accepted in our program, you have a guaranteed support for 5 years. With We waive the tuition. You do not pay the tuition to go to the university, and you are paid about $25,000 as a stipend to carry on your research. Huh? When you start, you are a teaching assistant, and what we want in exchange of when you are a teaching assistant, you have 12 to 15 hours of work every week, either doing undergraduate general chemistry lab or organic chemistry laboratories. Huh? And then we provide also students award. We have a number of awards for the best students, and we provide also travel support for students to go and contribute or participate in national and international conferences. Huh? So if anyone who is interested here, please feel free to contact Amanda Jones. She is the director of our graduate program, and this is her email address if you like. Huh? Now, in terms of research, I have, as the Dr. Luciane mentioned, I have actually a total of 4 projects in my lab. The first one is very fundamental in nature and deals about figuring out how to put molecules together to achieve certain properties, whether it's chemical properties and physical properties. And when I say molecules, we are talking about really very, very big molecule. We call them clusters. This cluster here contains metals and non-metals. And then we really go in the lab and play with the chemistry to try to figure out how do we put these molecules together and study their magnetic properties, their porosity, their electrochemical characteristics, and so on. Huh? The second project that has been active in my lab now, I say probably 12 years now, is developing catalyst to take waste and convert that waste to fuel. And the third one is what I would call heterogeneous photocatalysis. I think I understand that Dr. Luciane deals, a group actually deals with this kind of topic. So in this case, what we look at is developing heterojunctions between two solids, two semiconductors, and then look at their activities and their performance in terms of splitting water to produce hydrogen. So the two topics that I have chose for you today are these two. So let's look at. I will start by. Let me do this on. I'm gonna go back here, and then I will reduce that. So I'm talking about the part one, which is heterogeneous photocatalysis. This is just the outline for part one. Number one, I will talk about hydrogen as fuel. I will tell you about the good and the bad for hydrogen. What are the problems? What are the potentials? I will talk about photocatalysis versus photosynthesis, a natural process here versus an artificial things that we are trying to do. Then briefly introduce semiconductor photocatalysis, or that concept of using semiconductors to do photocatalysis. I'll talk about the challenges or the issues we have in these systems, and then the solutions that people have been working on for a long time. I will briefly talk about or describe three types of heterojunctions that can take a catalyst and make them visible, light active, or active in the visible light. Then I will share with you one case study that we have done. So the motivation, of course, of all this is the carbon issue. So this is a statement that came out just recently. It says, over the weekend, the climate system sounded simultaneous alarms. Number one, near the entrance to the Arctic Ocean in northwest Russia, the temperature surged to 84 degrees. And when we say 84 degrees, we're talking about Fahrenheit, 84 degrees Fahrenheit. Meanwhile, the concentration of carbon dioxide in the atmosphere exceeded 415 ppm for the first time in human history. Look at these. This one is from NOAA, and it comes from the Mauna Loa Observatory. This is located in Hawaii. And it shows just the changes in terms of CO2 concentrations in the atmosphere between 2015 and 2021. I mean, until today. And what you can see, I think it's better just to look at the black line. This is the average, and you can see straight increases from 400 or a little bit below 400 to a little bit actually above 415 today. There is a slight dip. You can see this dip here, and that is actually the effect of the pandemic. The more recent, in the most recent month. These fluctuations you see in red of the carbon dioxide concentration are due really to basically trees and leaves in the trees. So when you don't have leaves in the trees and start to increase, and you go up, let's say around this time of the year, especially in the northern hemisphere, there is not much green or chlorophyll is missing. You see very high CO2, and then when you reach the spring and you start having leaves, it goes down to a minimum and so on. That's why these consistent fluctuations of CO2. But the bottom line, what's important for all of us to know is that the carbon dioxide and the carbon is a huge problem. So it is really the main motivation of our work and the work of, I would say, the majority of people today. Now, the question is, what is really what are solar fuels? And beautiful chart I found in this reference. This is a recent paper by R.J. Datz in Energy and Environmental Science. This is the DOI to the paper. But what you see actually is it's interesting because if you take water on one hand and carbon dioxide on the other, so water here, carbon dioxide here, and you use solar energy, you can actually see all these kinds of applications. So the first one, we can actually use solar energy as just to concentrate solar energy on a tower here that contains water, so you generate heat. We refer to that as just thermal conversion, converting heat into different kind of biofuels. Now, the other thing that you must be really more familiar with is taking photovoltaic cells or wind energy, converting that to electricity, and then using that to do electroconversion or using it to produce heat and then doing thermal conversion. On the natural side of the picture, when you're using now carbon dioxide, you can do natural photosynthesis. So this is what I was talking about before. Photosynthesis is an amazing sink actually for carbon dioxide. So you can generate biomass, and that biomass you can use it to produce electricity, or you can do bioconversion to produce renewable fuels. On the other hand, you can microorganisms can do two things: photoelectrochemical cells, or if you have solids like what the topic I will be covering today, we use actually photocatalytic powders or microcrystalline materials to mimic, sometimes to mimic what we call the artificial fuel, artificial leaf. So if you do that, what you end up, you are using renewable energy, mostly solar energy, applying it to water, CO2, or a combination, and you can form all kind of either fuels on this side or organic materials with higher value. Now, I will focus from now on only on hydrogen. And for this part one, and part two, I will talk about biofuels. So let's look at hydrogen as a fuel. Why hydrogen is so interesting and so important? The number one rationale for hydrogen, and it has the largest mass-specific energy content. And you can see this in these three characteristics. Number one, when you burn hydrogen to form water, the free Gibbs energy is about 300 kilojoule per mole, meaning that we get about 300 kilojoule for every 2 grams of hydrogen. Compared, for instance, if you were to burn just carbon, I believe the delta G, or the free Gibbs energy, if you look at carbon plus oxygen given CO2, that's about 400, I believe, 400 kilojoule per 12 grams, versus here we have 300 kilojoule per 2 grams. So it has by far the largest mass-specific energy content. And we can do a back of an envelope calculations for an average car. It will take, it produces, well, let me actually go this. In terms of comparing hydrogen, or the amount of hydrogen you will get, amount of energy you will get for 1 kilogram of hydrogen versus 1 kilogram of gasoline, you get about 120 megajoule per kilograms of hydrogen, compared to only about 44 megajoule per kilogram for gasoline. So 3 times as much energy. And last one is this: you need only 4 kilograms of hydrogen to drive a range of 400 kilometers. You need a lot more than that in terms of gasoline. The second maybe positive thing about not maybe, but for sure. Second most important thing about hydrogen is the fact that the product of combustion of hydrogen is only water. And here people can argue. There are arguments, of course, because lots of people argue that water, of course, is a greenhouse gas. And maybe when we produce too much water, we get also climate change effect from excess production of water. But still, it's not as bad as producing carbon dioxide. And then, of course, as you most know, most common fuel used for fuel cells is still hydrogen. Now, let's look at the bad side or the problems with hydrogen that we currently have. Number one is that 96% of hydrogen currently produced in the world, 96% of it, is produced from fossil fuel. Coal, 18%, 30% from oil, 48% from natural gas. So the idea that we can use hydrogen, or by using hydrogen we are using clean energy, is not completely true, because currently most of it is actually produced by using fossil fuels. Only 4% of it is produced by electrolysis, using electricity. Here's the other problem. As I said before, you need about 4 kilograms of hydrogen to go or drive for 400 kilometers. Well, at 1 atmosphere, at atmospheric pressure, that 4 kilogram of hydrogen will occupy 50 cubic meters. Here I found this picture that actually helped us maybe better. This is the size of, you take hydrogen at 200 bars. So at 200 atmosphere, this is the size of the container of hydrogen you will need for this particular car to drive for 400 kilometers. So it's not really, we are having big issues there. If you take it and put it liquid, which takes a lot of energy, you need this size. These are compounds, we refer to them as hydrides, that are being also investigated as source of hydrogen. In other words, you put aluminum hydride in a container like this, and you can burn it to decompose it to provide hydrogen, and then that hydrogen is used to drive the car. So I show you the good and the bad, and it seems like this is amazing, maybe something that is new, but the fact is that if I go back to this, it goes back actually to Jules Verne. I'm sure many of you have read Jules Verne, many books of this amazing and interesting writer. So back in 1874, he wrote this L'Île Mystérieuse. He said, "Yes, my friends, I believe that water will one day be used as fuel, that hydrogen and oxygen, which constitute water, used either singly or together, will furnish an inexhaustible source of heat and light, of an intensity of which coal is not capable." It just says a lot about, not just about the man, about Jules Verne, but about the fact that people over time and for a long time have dreamed and imagined the use of hydrogen as a source of fuels. And so this is really nothing new. We are not creating anything new. It has been there around for a long time. Now, I want to compare the photosynthesis process to the photocatalysis process. So on the top here, we have the photosynthesis, the thermodynamic schematic diagrams for it. So as you know, photosynthesis is about taking carbon dioxide, mixing it with water, you produce glucose, and you release oxygen. This is the key by which trees and by which Amazon is so critical to the life on Earth, and that's why we call the Amazon forest I have the French word now in my mind, but not the English word. Very interesting. But it is the breeding mechanism by which really we take all those trees and the forest take carbon dioxide from the atmosphere, they mix it with the water, they produce glucose. But if you look very carefully, this system here is uphill. So this is the energy of the starting materials, and this is the energy of the product. It is an uphill reaction from the thermodynamic point of view. It takes energy to get there. Yet nature does it in a beautiful and so simple way. I mean, it's not that simple, but it does it every day, every minute, every second, every femtosecond. Nature does that, as long as we have leaves. The photocatalytic process for water is the same. We're taking water here. This is the energy for water. If you want to split it and form hydrogen and oxygen, this is the reverse reaction of the combustion of hydrogen to produce water. It takes about 200 kilojoule per mole. Here, by the way, this barrier in terms of energy is 10 times, almost 10 times this. It's about 23,000 or 2300 actually, that kilojoule per mole. So now in terms of the history of semiconductors as catalyst for photocatalysis, this was actually the first time it was reported, and most of you know this. It was by the group of Japanese, Fujishima and Honda. I think Fujishima is still alive and has a beautiful and very productive center in Tokyo. But in 1972, these two scientists reported in the magazine Nature the use of titanium dioxide under light. This is in the UV region. So if you take an electrode here and you put TiO2 on it, and then you shine UV light, you actually produce electrons, and those electrons can be used to either here to come and do the reduction of water to produce hydrogen, or do it also for the oxidation of water to produce oxygen. So in first step, TiO2 plus light produce electron hole pair. That electron, the holes are used to oxidize water to form oxygen, and the electrons are used to reduce the protons to form hydrogen. All this is being done at a platinum electrode. The overall reaction is 2 water molecules produce oxygen plus 2 hydrogen molecules. So that's what they have reported, and the explanation that they have given since is what we talked about. So if you take any solid, well, not any solid, but solid that have extended structures, and this is a particle here in blue, you know that there is a valence band, and there is a conduction band, and there is a band gap between them. If I shine a certain electromagnetic waves on them, you can promote an electron from the valence band to the conduction band. When you do that, you create electron hole pair. Then the electron is used to do the reduction, while the hole is used to do the oxidation. Now, there are the process, of course, there is a 3-step process. There is excitation. So when you excite, you form the holes, the electron hole pairs, and those, they have the choice. There are 2 mechanisms. They can either recombine. If they recombine, then they do not exist anymore. It's over. Or they can migrate. So this step 2 is migration. The hole migrates to the surface. The electron migrate to the same surface, of course. And then they are both involved in surface chemical reactions, electrochemical reactions that we can choose to apply it to different processes. So since their discovery, since the discovery of the first photocatalytic semiconductor in 1972, many different, and I'm listing only. This is a very limited, frankly, systems that is in this paper of 2013. But you can see that even though it's limited, it's still quite a number. So what do we have here? We have can see that there are three areas. Number one, all these here are active only under UV radiations. These one here in the middle are not stable. They are not stable chemically in water. They are not stable physically in water. And these are not suitable for the kind of either oxidation or reduction. And you can see that, for instance, if you take tungsten oxide, this tungsten oxide can do the oxidation, but doesn't have the physical characteristic to do the reduction. Likewise, this gallium arsenide, it can do the reduction, but it cannot do the oxidation. So, and there are a large number of these species. Now, what are the major challenges? We have two major ones. Of course, the absorption range is one of the first problem. As I said in the previous slide, most of them are active only under ultraviolet light. So we would like to have systems or semiconductors that are active in this area. As you can see, the UV here in kind of magenta color represent only about 5% of the total solar spectrum, while the visible is about 45%. So if we can take a semiconductor and make it active in the visible, we can actually enhance our production or our activity by as much as 10 times, and that will be superb. The other problem that we face is the lifetime of the photo-generated electron-hole pairs. So as we said before, this electron hole have a tendency, they thermodynamically as well as kinetically, the recombination of the electron and the hole is favored. So this combination of these two things lead to very low efficiency. In fact, I think the efficiency of the first system that Honda and Fujitsu reported was less than 2% the first time they reported that. So of course scientists try to find ways to work around this. Can we make these catalysts perform better? Let me stop here and ask you two questions. Number one, are you able to see my slide well now? Hello? Hello?
Sorry.
Are you?
Yes, very well.
Okay, and are you able to hear me well?
Yes, very well.
Oh, perfect. Huh? Thank you, Luciane. So the first thing that has been tried is to use actually metals as co-catalyst. So this is in light blue. I represented the semiconductor particle, and in dark blue you can attach what we call a co-catalyst, but generally they are metal, and most time it's platinum. So we put particles of platinum around the particle of semiconductors. So when you generate the electrons, those electrons move directly to the metal particle to do the reduction. And in such a way, when you do that, you are separating the holes from the electrons and maybe allowing for better lifetime for them to do the work. The second, and this is really nice actually, we call it band gap engineering. So when you take a semiconductor, you can either dope it with a metal ion, or you dope it with an anion, either a cation or an anion. So when you do that, you can change the gap, and if you are really successful, you can bring the gap from being a large band gap semiconductor to a relatively smaller band gap semiconductors, and hopefully you'll make it also active and divisible. Many researchers and papers have been described or have described this method. The other method that is really interesting is referred to as sensitization. So you can do sensitization by using a dye. So if you put a dye particle on semiconductor, then the dye absorbs the light, visible light. You generate the electron on the dye, and then that electron gets transferred to the conduction band of the semiconductor. Then the reaction can proceed that way. The other interesting, this was discovered also a number of years ago. Actually, we got to it relatively recently compared to I think the first paper to be published on heterojunctions go back at least 20 years ago. And that is, instead of using a dye, we're going to use another semiconductor. So you link one semiconductor to another. And one semiconductor can be, and I'll go into more details on next slide, but you can create what we call heterojunctions. And as the methods of synthesis developed, chemists and physicists could work together to develop different kind of systems. So let's look at what chemists and physicists have developed. There are three ways. Will this make this a little bit bigger? So there are three types that you can make. So type 1, you can take a visible light active semiconductor and connect that to a UV active component. So this one here is a visible light active semiconductor, and this one is a large band gap semiconductor. When you shine light, visible light, you gonna create holes here. Electrons are promoted to the conduction band of the first semiconductor. Since the conduction band of the second semiconductor is lower, then electrons will go downhill. And now what you end up doing is having electrons mainly on this semiconductor and holes mainly on this one. So you separated the electrons from the holes. The type 2 is actually you use two visible light active components. So you shine visible light on both. You create holes and electrons here, holes and electrons there. But since physically electrons go downhill and holes go uphill, you end up with same result actually as here, which is separation. Electrons on this semiconductor and holes on the second semiconductor. And then last one, the most complicated one, is this one. We call it type 3 or Z type of mechanism. So in this mechanism, both of them are visible light active, but as you see, the conduction band of this semiconductor is lower than the conduction band of this one. So when you shine light, you create electron pair holes here, electron pair holes here, but the electrons here are, in fact, actually this is not an ideal presentation, but representation, but this level is actually a lot closer to this one here. So electrons go and they find these holes to remove them. Basically, they recombine with these ones, and the result is that you end up electrons there and holes there. So all these three type of schemes and mechanism deal with separation of the electron hole pair, and of course lengthening the lifetime of these two. So here we're gonna show you, or I'll show you, we worked actually in all these three types, type 1, type 2, and type 3. And for the sake of time, and we publish all this work, so you can go and check it out if you're interested. But I will pick up this because it represents some interesting characteristics. So I will focus from now on only on we took a graphitic carbon nitride, G for graphitic, C3N4, and we made a heterojunction with a compound called strontium tantalum oxide. So this heterojunction, number one, maybe I should give you why did we choose it, yeah? Let me make this. So what is the rationale for choosing this particular heterojunction? Well, the number one rationale is the fact that we can make it. So when we went and tried it, of course, you try always a lot of different systems, and frankly, many systems, it's difficult to make these heterojunctions as true heterojunctions. So in this case, it worked well because we could do it in situ, and I will show you in details how we make it. So it's an in situ formation of this heterojunction. This compound itself, this component, is actually a metastable oxide. It's not a stable oxide, and then I'll show you the crystal structures of these materials. Second important point is that it can be made at relatively low temperature. We'll show you how we use the technique of chimie-douce, or soft chemistry, to actually make these materials. And then it allowed us actually, I would not show this in details, but it allowed us to study the photocatalytic properties of a series of materials at the same time. And of course, we would not have chosen to work on this system if somebody else has already done it. So here is an interesting picture here. This is just showing where the band gaps or the band levels of each semiconductors are located. And if you concentrate only on the first one here and the last one, those are the two most important things for this talk, you can see that the band gap for graphitic carbon nitride is about 274, so that's indivisible. The band gap for the STO, strontium tantalum oxide, that's 394, that's in the UV. So not only that, but it's interesting, these lines here are where the oxidation of water and the reduction of water occurs. So both positions of the band are appropriate to do either either the reduction or oxidation of water. Now, how do we make these? This slide is relatively busy. Let me see if I can move it. Yeah. So this is about making the heterojunction. So look at this here. We start with solid potassium citrate. We mix it with tantalum oxide and strontium nitrate. We heat this mixture, we grind it first, and we heat it at about 1000 degrees centigrade for 12 hours. And if you do that, you make potassium strontium tantalate. In order for us to actually get to the material we want, we do hydrogen exchange. So if you take this powder that is white, and then you do ion exchange using 4 molar nitric acid, and you put that for 4 days, you end up in exchanging all the potassium for hydrogen. So you make an acid form. And interestingly enough, the crystal structures is different. Even though it's a simple ion exchange, in fact, you form a different crystal structure. And here, once we make this, we mix it with melamine, and we just grind it and in water or acetone. Then we put all this mixture in an autoclave to do hydrothermal treatment at 200 degrees centigrade. And once you do that, you actually form this kind of mixtures, white, gray material. And then if we heat it about 550 degrees centigrade, we get our heterojunctions. So it's rather long and complicated, but at least so it allows us to make the heterojunction. So take you step by step through the crystal structures parameters for those who are interested. And I wanna emphasize one thing here that is really important. The physical as well as the chemical properties of materials has to do with the crystal structure of materials. There is a direct, so if we can understand the crystal structure of materials, we can certainly make assumptions as to the physical and chemical properties. And fortunately, this is a part of, we call it X-ray crystallography, that is dying. Many schools do not teach crystal structures or crystallography, or if they do, it's still, there's a, I'm sure maybe at your university there is a lab that has a single crystal diffractometer, and there is a person who deals with making it, and students generally do not know, frankly. At least our students, I tell you, my students do because they have to do it, but most of our graduate students do not learn X-ray crystallography, and that's unfortunate. Anyway, so you take, this is the crystal structure of the strontium tantalate. This is actually the crystal structure of the acid, and this is the crystal structure of the final material that we obtain. You can see this is tetragonal. It stays tetragonal. This is the symmetry of the system, and it becomes a cubic. This is the hexagonal structure of the carbon nitride. So I said it's metastable because this is stable up to 850 degrees centigrade. If you heat it above that, you get a different structure. Same formula, but a different structure that is not, cannot act as a catalyst. And this is shown in the next slide. So this is the X-ray powder diffraction of the systems. So this is what I call HSTO. This is the acid form. So it has these peaks here. As we heat this compound at 350, all the peaks are maintained, so it's stable. 450, it's okay. And then 550, it changed. This has disappeared. This one has disappeared. And we start this maintained because we are having a structure that is related to this one, but we start actually making a completely different material here. And as you heat to 750, this is the crystal with the powder diffraction of STO. It's still STO, same structure at 850. Once you go to 900, you are obtaining what we call tetragonal tungsten bronze structure. This is the tetragonal phase, while this one here is the cubic phase. So what we wanted is actually this phase. So we can heat up to 850, and we see as low as 550 or as high as 850 without having any issues. Now, when we made the heterojunction, we needed to prove that we have the carbon nitride as well as the STO in it. So we take another X-ray powder diffraction of each component. This is the X-ray powder diffraction of carbon nitride. This one in black is actually the powder diffraction of this STO, and that's portion of this one here. And then this one is a mixture of carbon nitride and STO, not a heterogeneous mixture, but an actual heterojunctions. And we will talk about what the difference is later on. But you can see this comes from that. This one, it shows up as very small one, and these here, there, and so on belongs to the STO. So this is just to prove that we do have a heterojunction. Of course, X-ray powder diffraction cannot tell you exactly that you have a heterojunction. It just tells you that you have the two component present. So we need some scanning electron microscopy and do EDAX analysis, meaning we do elemental analysis to see. So this is a rather large particle of the heterojunction. And then we do imaging or elemental analysis. So here in the red, it shows you, do you see the red well on your end? Okay. So we have the red particles just show that we have the present, or the red dots means strontium is present. The green shows the distribution of tantalum, and then the blue, sky blue, actually shows that we have the presence of nitrogen. So by combining these things and the fact that they are so homogeneously distributed, it tells us that we do have a true heterojunction. However, we need to go even further and look at one crystal. So we identified one crystal here, and we looked at the elemental analysis, and we colored here. So you can see around here in a kind of blue-purple color is the nitrogen, and inside we have the red and the yellow for tantalum and strontium. So this proved that we do have a really good heterojunction between carbon nitride and tantalum oxide. Furthermore, we need to prove that there is an actual linkage between the structure of tantalum oxide and the structure of carbon nitride. So we do XPS. So this is a XPS for the heterojunction. And what you see, it's very interesting actually. So you look at the carbon 1s in carbon nitride, red, versus the blue one, which is the heterojunction. And you can see it went to lower energy. Likewise for nitrogen 1s, lower binding energy. Likewise for tantalum 3D, you can see it went through lower binding energy. This tells us that there is a true connection between, and I'm talking about binding connection, between the carbon nitride on one hand and then the tantalum oxide on the other hand. Then, of course, we looked at we do diffuse reflectance spectroscopy, and then valence band XPS. So on the left side, here on this side, we have the actual diffuse reflectance spectroscopy. So I will just focus on the carbon nitride is here in red, and the heterojunction is right there. So it looks like we took a STO, or not like STO, but STO, the black one, which is right here, and that band, at least the absorption, has moved toward the visible dramatically. We do valence band XPS to experimentally determine the positions of the bands. So if you do valence band XPS, and here is the one for carbon nitride, and this is the one for STO. If you do it properly, you find that for the binding energy for STO is at 3.35, and the binding energy for carbon nitride is at 1.64, and that tells you what the band gap is. That's why we call it valence band XPS. So if you do that and then you combine it with this empirical formula, we can actually get the positions of the bands in each one of the semiconductors. So here we calculated that the conduction band for carbon nitride is at minus 1.10 electron volts. Valence band is at plus 1.64 electron volts. And that allows us to, if you if you look at the numbers, actually this 1.64 and 3.35 are the positions of the valence band. And knowing what the EG is, you can determine what the conduction band is and determine whether they are suitable or confirm what happens. So if you do that, you find that the confirm actually that STO is in the UV 3.94. But we have actually extended the absorption range from 3.94 to almost 1.64 for which is the band gap for carbon nitride. So let's look at the performance then. I mean, that's what the goal was, is actually study what the performance of this heterojunction is. So on the left side there is a table that just tells you the amount of hydrogen per gram that was produced by per gram of catalyst. So under UV light, for the STO, can form 216 micromole per hour. Carbon nitride produce 174 micromole per hour. If we expose STO to just visible light, we got nothing, and we know that it's not active. It shouldn't be active in the visible given the band gap. But for carbon nitride, we get 156 under visible light because it's yellow. It absorbs in the visible. For the heterojunction, under UV, we produce 874, while under visible light, we produce 744 micromole of hydrogen per hour. So if we just compare the performance or the production of hydrogen per mole per hour to that of carbon nitride, we got about 9 times more than, or better performance than this. This doesn't mean it's really an amazing heterojunction. It's just a study that we have done, because if we look at the quantum efficiencies, yes, it has been better, or the overall apparent quantum efficiency or quantum yield as we call it, we get from 0.35 for carbon nitride alone, we go up to 2.62% for the heterojunction. So it's a superb enhancement in the performance, but it's really nothing to we cannot say that this heterojunction can be used practically, but it proves the point that heterojunctions are extremely useful in this kind of processes. So on the right side, we looked at the time of irradiation using visible light compared to the amount of hydrogen produced. And you can see here in black is STO. So of course nothing is produced under UV light for STO. For carbon nitride, the red line here. And for the we took a mixture because we wanted to make sure that there is a heterojunction. There is a difference between formation of a heterojunction and the activity of that heterojunction versus just mixing two powders together. So this is what I call here the blend. We mixed carbon nitride powder with STO powder. We grind them and we use them to produce hydrogen, and this is the performance in green. Compared to the actual heterojunction which is there. So a huge difference between the blend in green and the actual heterojunction. Now, it's not sufficient to show this. What is also important is to study the stability of these heterojunctions. So we have done two things. Number one, just cycling. This is the first cycle, second cycle, third cycle in terms of irradiation. So each cycle lasts for about 5 hours, and we look at the hydrogen evolution. And as you can see, they are identical, or almost identical. It's very difficult to differentiate one from the other. We have done, since this study, we have done many more cycles just to see, well, how long does it last? And so far, we have noticed no change in the actual performance. On the right side, we looked at the X-ray powder diffraction. The black is before these cycles, and the red is after the cycles have been done, and you can see there is no dramatic difference between the two. So in summary, what I can share with you is that these semiconductor heterojunctions are a potential solution to both the absorption range, meaning bringing something from the UV to the visible absorption range, as well as the recombination rate. The carbon nitride STO heterojunction has led to an enhancement of about 9 times the actual production of hydrogen from carbon nitride under visible light. We can actually use these again in terms of doing efficient charge separation. As a message for you and for people who are interested in this topic, to design good heterojunctions, we need to pay attention to selections of materials is the key. Not only the nature of the materials we use, but also their stability, their long-term stability. We need to look at their band positions, and that comes from knowing the crystal structure and doing calculations, band structure analysis to determine whether the bands are accurately positioned for the purposes that we want. And then, of course, the key is actually finding the right way to make these heterojunctions. Is by far the most, I would say, the bottleneck in this project is developing the right synthetic methods to make true heterojunctions. So this is the end of the first part of my talk. Luciane, you want me to stop now and answer questions on this first part before I move to the second part, or whatever you like to do? Hello.
Oh, hello. Hello, I'm here. I think it's good to finish here because someone has some question. I have some question.
Okay, good.
Okay.
So I'll stop here and then I'll answer what I like you to do. If you or any one of you can read the actually chats and then maybe repeat them for me, and then I can answer the question. Okay.
Okay, and maybe the other conference you talk about the next topic.
That's okay. That's great.
The other topic. Okay.
Oh, yeah, we can do it as another time. You mean another time?
Yes.
Okay. Yeah, you're right.
Okay. Oh, you will go to Aracaju, Sergipe next pandemic, and talk about the other topic.
About the other one, I agree with you actually, because it must be very late for you there, huh?
Yeah. Yes.
Yeah.
Ok.
Uhum.
João, oi. A gente vai abrir agora para algumas questões. Se alguém tiver alguma questão para fazer, João, como é que faz para abrir aqui as... Isso. There is a question here, Abdou, Dr. Abdou.
I have a question. Since the individual compounds are not chemically modified, why are the DE signal in C1 and N1 shifted to smaller molecule values? That's a very good question, exactly. Yeah? So the binding energy, if there was no change, if there was no chemical connections between the two layers of the carbon nitride and STO, we should expect the binding energy not to change at the surface. And we're talking about the linkage between the two species. If and that is the case, I should probably have added the picture of the XPS for the what do we call that, the actual blend when we just make the powder You're exactly right. There is no change, there is no linkage between the two materials, and we see the binding energy for either the C1s or the N1s do not change at all. But here, since it's going towards smaller or lower binding energy, it means, to me anyway, it means that there is a true binding between the carbon nitride semiconductor and the STO semiconductor at the surface, not inside material, but at the surface between the two particles. Did I answer your question correctly?
Okay, and I have a question.
Please.
The performance with semiconductor heterojunction is the visible light is good, okay,
Yeah.
but the synthesis is large, complicated. My question is it possible to synthesize the simple synthesis and the other
Yeah.
heterojunctions simple?
Yeah. 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 There is probably ways to do it simpler than that. I would say there is a method that is referred. I'm sure you know about this. The co-precipitation method. You can co-precipitate. You form what we call a sol gel, and then from the sol gel, you can heat it up to produce a more crystalline material. This perhaps a better way to do it. I was just presenting the one that really worked for us, huh? And I think once it's very interesting actually deal. As I said, it is making these materials is the most not the most difficult part of the work, but certainly the one that takes a lot of trial and error, because when we used other methods, at least when my students used other methods, what we ended up making are mixtures of other systems. And that's why we needed to go by using this complicated method in order to get to the heterojunction that we want. Huh? Yeah.
Okay. The other
I have
question.
I have a question from Marcelo here. Thanks for this. Regarding the hydrogen sources, do you think is it possible to have a new source of it other than fossil fuels in the near future? Yes, I do. I really do, and I think making it from water will be ideal. But if it is not difficult, then I think solids like aluminum hydrides, nickel hydrides can be used as a source to when you do a decomposition. Lithium, what is it called? Lithium nitride. Because what happened, lithium nitride, when it's exposed even for little, very little time to water in the atmosphere, it make an amide, and then people looked at making lithium amide and decomposing lithium amide to form hydrogen, and then you can expose the lithium back to nitrogen under normal, I mean normal, it's not that normal, but under low temperature, about 180 degrees, and you make lithium nitride, and you go back and forth between the two. Huh? That has been reported, and it is actually may work very well in the future. Eh?
Abdou,
Yes.
the Dr. Valnice uses the electrochemical systems. Yeah?
Yes. Yeah.
And she uses two different compartments.
That's correct.
In the one use the oxidation of the compounds, and the
Mm-hmm.
other one is on the cathode.
Mm-hmm.
Okay, the your system you use only one compartment?
Yes, indeed. Yeah, very good point. We use only one compartment, and we use a cell. I should have put the picture of or a photo of the cell. We use a quartz cell. We put our powders in the water. We bubble nitrogen to remove any excess hydrogen, and we use what we call a sacrificial electrode. So we are a sacrificial anode. So we add, what is that we add? Methylamine. I don't remember exactly the compound, but it is one that gets oxidized during the actual reduction. It's true. Yeah. Yes. Yes, we do.
Okay.
But
I understand you.
Yeah.
Methylamina.
Methylamine.
Yeah, methylamine in English.
Yeah.
Okay. Yeah. Okay. Yeah. I have other question, Zeca. No, I think no. Dr. Abdou, thank you so much. It's very pleasure here you. The graduate program thanks you for participating in this event, and I wait to visit you or you visit me in Aracaju. Thank you so much.
You're always welcome to visit us here, and as well as your students and your colleagues. So we will be happy to host you. It's a beautiful place, and it's a beautiful university. You need to talk to Valnice, who visited us a couple of years ago.
Yeah. Okay. I have students. My students go to visit. We'll go to visit you briefly.
Perfect. I will be happy to host them, and I'm also looking forward to have better news of the situation in Brazil with all the pandemic that is going on. I hope your students are still productive in this kind of environment. So.
Yes, it's very difficult the situation here, and I think in USA too.
In the USA, it's our productivity has gone down for sure. We are not as productive as we used to, and that has been the case for since it started, since March. So our students now actually are gone. The undergrads, they went back home so we are pursuing the teaching for this week and next week, just about through online communication.
Okay. Here too.
Okay.
Here too.
And are you still able to go to the supermarkets and walk around without mask, or you have to wear masks?
No, use mask.
Okay. Good.
Okay.
Well.
Okay. Thank you very much.
Yeah, thank you, and enjoy the weekend. Okay.
Okay. Your candy. The kiss your wife.
I will. I certainly will. She will be happy.
Bye.